soft ambient music fades in slowly. Hello, Midnight Wanderers. Welcome back to the Midnight Explorer. Tonight, we're going somewhere different, somewhere quiet, somewhere vast and impossibly dark. Close your eyes for just a moment. Imagine standing in a field on a moonless night, far from any city lights. Above you, the stars spread out like scattered diamonds on black velvet. Beautiful, isn't it? Peaceful. But here's something that might surprise you. Everything you're seeing, every star, every planet, every galaxy blazing across that cosmic canvas, all of it, all of the light, all of the matter we've ever touched or seen or measured, makes up less than 5% of our universe. Less than 5%. The rest? The remaining 95%? It's hidden, invisible, a cosmic mystery that has haunted scientists for nearly a century. Tonight, we're going to explore that darkness together. Not with fear, but with wonder. We'll journey through the minds of the astronomers who first glimpsed this secret, walk alongside the physicists who dared to question everything they thought they knew, and stand at the edge of our current understanding, staring into the beautiful, terrifying unknown. So settle in, dim the lights, let's explore the dark side of the universe together. Music transitions to gentle, contemplative theme. Our story begins not in a laboratory, not in a university, but in the mountains. It's 1933. The world is caught between two wars, still reeling from the Great Depression. In California, perched high in the San Gabriel Mountains, there's an observatory called Mount Wilson. This isn't just any observatory. This is where Edwin Hubble recently discovered that our universe is expanding, where the very fabric of reality was being rewritten with mathematics and light. And on this particular night, a Swiss astronomer named Fritz Zwicky is staring through a telescope at something that will change everything. Fritz Zwicky. Even his name sounds like someone from a bedtime story, doesn't it? But Zwicky was real, very real, and he was about to stumble upon something that would haunt physics for the next century. Zwicky was observing something called the Coma Cluster, a vast collection of galaxies, more than 1,000 of them, bound together by gravity, spinning through space like a cosmic dance. Beautiful to observe. Mathematically, it should have been simple to understand, but it wasn't. See, Zwicky was measuring how fast these galaxies were moving. He watched them spin and swirl, calculated their velocities, and then, as any good scientist would, he did the math. He added up all the visible matter in these galaxies, the stars, the gas, the dust, everything he could see. Then he calculated how much gravity all that matter would produce, and finally, he checked whether that gravity would be enough to hold the cluster together. It wasn't. Not even close. The galaxies were moving too fast, far too fast. According to his calculations, there wasn't nearly enough visible matter to keep them bound together. They should have flown apart long ago, scattered across the universe like dandelion seeds in the wind. But they hadn't. They were still there, still dancing together in their cosmic waltz. Zwicky sat back and considered what this meant. There were only a few possibilities. Either his calculations were wrong, unlikely, he'd checked them multiple times, or the laws of gravity were wrong, possible, but Newton and Einstein both couldn't be that far off, or there was something else there, something he couldn't see, something invisible, adding mass, adding gravity, holding everything together. He called it Dunkel Materia, dark matter. Imagine being Zwicky in that moment. Imagine looking up at the night sky and realizing that most of what you're looking at isn't really there. Or rather, that most of what is there you can't actually see. It would be like walking into a room full of people, but being able to see only their shadows. How would that feel? Unsettling? Exciting? Both? Zwicky wrote up his findings. He published his paper, and then almost nothing happened. The scientific community largely ignored him. Zwicky had a reputation, you see. He was brilliant but difficult, prone to calling his colleagues spherical bastards. A wonderful insult, meaning they were bastards no matter which way you looked at them. He made enemies, he was abrasive, and sometimes when someone is hard to work with, their ideas get dismissed along with their personality. So dark matter sat there in the pages of an obscure journal, waiting for nearly 40 years before anyone would take it seriously. But the universe kept its secrets. The galaxies kept spinning too fast. The evidence kept accumulating, silent and patient as starlight. Now, let's move forward in time. It's the 1960s and 70s. The world has changed. We've sent humans to the moon, computers are beginning to transform society, and the Vietnam War is dividing nations. In this changing world, a woman named Vera Rubin is doing something revolutionary, though she doesn't know it yet. She's looking at galaxies, really looking at them. Not just at them, but into them, measuring how they spin. Vera Rubin grew up dreaming of stars. As a young girl in Washington, D.C., she would lie awake at night watching the stars move across her bedroom window. She built her own telescope at 14. She knew, with the quiet certainty that some people have about their purpose, that she wanted to study the cosmos. But being a woman in astronomy in the 1940s and 50s wasn't easy. Princeton didn't accept women into its astronomy program until 1975. When Rubin called to inquire about graduate school, she was told, simply and directly, that women weren't allowed. She went to Cornell instead, then to Georgetown, building her career stone by stone, fighting for every observation, every hour of telescope time. And then she started looking at spiral galaxies. You know spiral galaxies, the classic cosmic pinwheel, arms of stars swirling around a bright center. The Milky Way is one. Andromeda is another. They're beautiful, majestic, and when Rubin looked at them closely, they were all wrong. Here's what should happen in a spiral galaxy, according to basic physics. The stars near the center, where most of the visible mass is concentrated, should orbit quickly. The stars farther out, with less mass pulling on them, should orbit more slowly. Think of the solar system. Mercury races around the sun in just 88 days, while distant Neptune takes 165 years. But that's not what Rubin saw. Working with her colleague Kent Ford, using a new sensitive spectrograph that could measure the velocities of stars with unprecedented precision, Rubin measured galaxy after galaxy, and in galaxy after galaxy, she found the same impossible thing. The stars at the edge were moving just as fast as the stars near the center. Imagine a merry-go-round, where the horses on the outer edge move just as fast as the horses near the center. Impossible, right? The outer horses would need more force, more energy. Something would have to be pushing or pulling them to keep them moving that fast. That's what Rubin was seeing in the galaxies. The outer stars shouldn't be moving that fast. Unless there was more mass out there, much more. Mass that extended far beyond the visible edges of the galaxy, creating a vast halo of invisible matter that pulled on those outer stars, keeping them spinning at impossible speeds. Dark matter. Again. But this time people listened. Rubin's observations were meticulous, repeatable, undeniable. She measured dozens of galaxies, then hundreds. The pattern held. Every spiral galaxy she examined showed the same flat rotation curve, the same evidence of invisible mass. The scientific community couldn't ignore this. A respected astronomer with careful methodology was confirming what Fritz Zwicky had suggested 40 decades earlier. There was something out there, something vast, something that made up the majority of the mass in every galaxy. Dark matter. But this time, people listened. Rubin's observations were meticulous, repeatable, undeniable. She measured dozens of galaxies, then hundreds. The pattern held. Every spiral galaxy she examined showed the same flat rotation curve, the same evidence of invisible mass. The scientific community couldn't ignore this. A respected astronomer with care. So, if dark matter exists, and the evidence was becoming impossible to ignore, what could it be? Scientists love to categorize things, to give names to the unknown. And so they started proposing candidates, giving them wonderful, imaginative names that sound like creatures from mythology. First, they considered the most mundane possibility. Maybe dark matter was just ordinary matter that we couldn't see. Machos, massive, compact halo objects. These could be black holes, neutron stars, brown dwarfs, or rogue planets. All things made of normal atoms, just not giving off light. Objects lurking in the dark spaces between stars, adding mass without adding light. Scientists searched for machos using a clever technique called gravitational microlensing. Here's how it works. When a massive object passes between us and a distant star, its gravity bends the star's light, making the star briefly appear brighter, like nature's own magnifying glass. If machos were out there in sufficient numbers, we should see these brief brightenings regularly. They looked. They found some machos, a few brown dwarfs, some dim stars, but nowhere near enough to account for all the missing mass, maybe 5% of what was needed. The vast majority of dark matter wasn't hiding in plain sight as ordinary dark objects. It was something stranger. So they turned to particle physics and proposed WIMPs, weakly interacting massive particles. Beautiful name, isn't it? WIMPs would be particles left over from the Big Bang, particles that barely interact with normal matter at all. They'd pass through your body right now, billions of them maybe, and you'd never feel a thing. They'd pass through the entire Earth and out the other side without even noticing. Imagine that. Imagine particles for which solid matter is as insubstantial as fog. We'd be ghosts to them, and they'd be ghosts to us, perceptible only through their collective gravitational pull. The search for WIMPs became one of the great experimental efforts in modern physics. Scientists built detectors deep underground, in old mines, under mountains, where the sheer weight of the rock above would filter out almost all other particles, leaving only the ghost-like WIMPs to potentially interact with the carefully prepared detector materials. These detectors are marvels of engineering. Some use tanks of liquid xenon, cooled to nearly 100 degrees below zero, watched by thousands of sensitive photomultiplier tubes. If a WIMP, just one WIMP, out of the billions passing through every second, were to bump into a xenon nucleus, it would produce a tiny flash of light. That's all. A single photon of light from a collision that occurs once in months of waiting. Imagine being a scientist working on these experiments. You descend into a mine kilometers underground, where it's absolutely silent except for the hum of cooling systems. You enter a clean room, don sterile suits, and check readings on detectors cooled to temperatures that barely exist anywhere in the universe. You wait. Days become weeks, weeks become months. You're searching for something that might not even exist, watching for a flash of light that might never come. And yet, they do it. Year after year, decade after decade. So far, despite decades of searching, despite detectors becoming increasingly sensitive, despite experiments scattered across the globe in Italy, in China, in South Dakota, in Canada, we haven't found WIMPs, not definitively. There have been tantalizing hints, anomalies that appear and then vanish, but nothing that holds up to scrutiny. Nothing that makes physicists say, yes, that's it, we found it. Then there are other candidates, each stranger than the last. Axions, hypothetical particles, so light they're almost nothing, yet supposedly so numerous they could account for dark matter through sheer quantity. Primordial black holes, tiny black holes formed in the first fractions of a second after the Big Bang, each smaller than an atom but containing the mass of a mountain. Sterile neutrinos, ghost-like particles even more elusive than the already elusive neutrinos we know exist. Each theory has its champions, its experiments, its dedicated researchers spending careers in pursuit of confirmation, and each so far has come empty. It's humbling, isn't it? We've built particle colliders that accelerate protons to nearly the speed of light and smash them together with energies that briefly recreate conditions from the first moments of the universe. We've sent telescopes into space that can see galaxies formed when the universe was barely 500 million years old. We've detected gravitational waves from black holes colliding billions of light years away. But we can't find the stuff that makes up 85% of the matter in the universe. Sometimes, late at night, I wonder what dark matter particles would think of us, if they could think. Here we are, made of ordinary matter, the minority, the rare stuff, searching desperately for them, the majority. We're like the 1% trying to understand the 99%, and we're failing. There's something almost poetic about that failure, something humbling. It reminds us that for all our telescopes and particle accelerators, for all our mathematics and our theories, we are still children looking up at a night sky we barely understand. Now, you might think that discovering most of the matter in the universe is invisible would be enough mystery for one cosmos. The universe, it seems, has a sense of humor. Let's travel forward to 1998. The world is on the cusp of a new millennium. The internet is transforming how we communicate. The Hubble Space Telescope is sending back images of breathtaking beauty. And two teams of astronomers are racing to measure something fundamental. How much is the expansion of the universe slowing down? See, we've known since Hubble's time that the universe is expanding. Every galaxy is moving away from every other galaxy, like dots on the surface of an inflating balloon. But gravity should be slowing that expansion down. Just like a ball thrown into the air eventually slows and falls back down, the universe's expansion should be slowing as all the matter in it pulls back on itself through gravity. The only question was, how much is it slowing? The two teams, the Supernova Cosmology Project and the High Z Supernova Search Team, had a clever way to answer this. They would look at distant supernova, exploding stars that are bright enough to be seen across billions of light years. A special type of supernova called Type 1a acts like a standard candle. They all have approximately the same intrinsic brightness. So by measuring how bright they appear from Earth, you can calculate how far away they are. And by measuring their redshift, how much their light has been stretched by the expansion of space, you can figure out how fast they're moving away. Plot enough of these supernovae from different distances, and you can map the expansion history of the universe. You can see how the expansion rate has changed over time. Both teams worked independently, gathering data, analyzing supernova, double-checking their results. This was important work, but they expected a straightforward answer. They expected to measure how much the expansion was slowing down. What they found instead shook cosmology to its core. The expansion wasn't slowing down, it was speeding up. Imagine their reaction. You measure something, certain you know what you'll find, and you get the complete opposite result. It would be like dropping a ball and watching it fall upward. It violates every intuition, every expectation. The teams checked their math, they checked their data, they looked for errors, for mistakes, for any possible explanation that didn't require them to completely rethink the universe. They found nothing wrong. The result stood. The universe's expansion is accelerating, getting faster. Something is pushing space itself apart, overpowering gravity, driving galaxies away from each other at ever-increasing speeds. But what could do that? They called it dark energy. And immediately you can see the pattern. First dark matter, now dark energy. two invisible components of the universe, both discovered by what they do rather than what they are. But dark energy is different from dark matter. Dark matter clumps together, creates gravitational pull, holds galaxies together. Dark energy is spread smoothly throughout all of space and it pushes outward, accelerating expansion. If dark matter is mysterious, dark energy is profoundly alien. The simplest explanation, though simple as a relative term in cosmology, is that dark energy is the energy of empty space itself. Quantum mechanics tells us that even empty space isn't truly empty. It's seething with virtual particles that pop into existence and annihilate each other so quickly we can't directly observe them. This virtual foam could, in theory, have energy. And if empty space has energy, then as the universe expands and creates more space, there's more energy, pushing expansion to accelerate. Einstein actually predicted something like this in 1917. He added a term to his equations called the cosmological constant, a kind of anti-gravity that could keep the universe static. When he learned the universe was actually expanding, he called the cosmological constant his biggest blunder and discarded it. Turns out, he might have been right the first time. But here's the problem. When physicists calculate what the energy of empty space should be based on quantum mechanics, they get an answer that's wrong by a factor of 10 to the power of 120. That's not a typo. That's 1 followed by 120 zeros. It's possibly the worst prediction in the history of physics. Yet something is accelerating the expansion of the universe. Something fills all of space. Something we call dark energy because we have literally no idea what it actually is. So let's take stock of our universe, shall we? When we measure everything carefully, here's what we find. Ordinary matter, everything we've ever seen, touched, measured, everything on Earth, every star, every planet, every galaxy, all the atoms that make up you and me, makes up about 5% of the universe. Dark matter, invisible, unknown particles that interact only through gravity, makes up about 27% of the universe. Dark energy, the mysterious force accelerating cosmic expansion, makes up about 68% of the universe. 5%. We understand maybe 5% of what the universe is made of. Doesn't that just fill you with wonder? And maybe a little bit of existential vertigo? We've built a civilization, developed technology, split the atom, landed on the moon, decoded the human genome, all using that 5%. We're like people who've explored 5 rooms of a 100-room mansion and declared we understand architecture. Let's slow down for a moment. Let's step back from the physics and the measurements and think about what all this means. For most of human history, we believed that seeing was understanding. If you could see something, touch it, measure it directly, then you could understand it. The ancient Greeks watched the sky and developed geocentric models of the cosmos, everything revolving around Earth because that's what it looked like. It took millennia to look deeper, to realize that appearances could be deceiving. But we still held on to the idea that reality was fundamentally something we could observe. Even as we discovered atoms and then electrons, then quarks, particles too small to see directly, we could still detect them, measure their properties, understand their behavior. Dark matter and dark energy challenge that assumption at a fundamental level. We can't see them. We can't touch them. We can't, so far, detect them directly. We know they exist only by their effects on things we can see. It's like being in a room with invisible people. You can't see them, you can't touch them, but you can see the chairs moving when they sit, see the doorknobs turning when they leave, hear the echoes of their presence. Is that enough? Can we say we truly know something exists if we can only ever perceive it indirectly? Philosophers have grappled with similar questions for centuries. George Berkeley, an 18th century Irish philosopher, argued that objects only exist when perceived. Esse ist percipi. To be is to be perceived. If you're not looking at something, does it really exist? Most of us would say, yes, of course things exist when we're not looking at them. The moon doesn't vanish when you close your eyes. Your house doesn't disappear when you leave for work. But Berkeley's question becomes more profound when we talk about dark matter and dark energy. These are things that cannot, even in principle, be directly perceived by human senses. They don't emit light. They don't have temperature we can feel. They pass through ordinary matter almost as if it weren't there. In what sense do they exist to us? Yet their effects are real. Galaxies spin in ways that require dark matter. The universe expands in ways that require dark energy. The mathematics is undeniable. The observations are consistent. To deny their existence would require throwing out a century of increasingly precise measurements. So we're forced into this strange position, believing completely in something we've never seen and may never be able to see directly. It's an act of faith, in a way, not religious faith, but scientific faith. Faith in the self-consistency of the universe. Faith that mathematics can describe reality. Faith that our instruments and observations, properly interpreted, reveal truth even when that truth is invisible. And isn't there something beautiful about that? Something humbling? For all our accomplishments, for all our technology and knowledge, we're forced to admit that most of the universe operates beyond our direct perception. We're like creatures who can only see in black and white, slowly realizing that the world is full of colors we can't imagine. There's a poem by Rainer Maria Rilke that feels relevant here. He wrote that perhaps all the dragons in our lives are princesses, who are only waiting to see us act just once with beauty and courage. Perhaps everything that frightens us is, in its deepest essence, something helpless that wants our love. Dark matter and dark energy frighten us a little bit, don't they? They remind us of our limitations, our ignorance. They show us that the universe is far stranger than we imagined, far less knowable than we hoped. But maybe instead of fear, we could choose wonder. We could see these mysteries not as threats to our understanding, but as invitations to dig deeper, to look further, to imagine more boldly. The universe has secrets. It always has. And some of those secrets might remain secrets forever. Some questions might not have answers, at least not answers we're capable of understanding. But not everyone accepts dark matter and dark energy as real things. Some physicists look at the evidence and see not mysterious invisible substances, but a sign that our theories themselves are wrong. What if, they ask, we don't need dark matter? What if gravity itself works differently than we think? This idea goes by several names. Modified Newtonian dynamics, or MOND, is one of the most famous versions. The basic idea is elegant. Maybe Newton's and Einstein's laws of gravity work perfectly fine at the scales we can easily observe, planets orbiting stars, objects falling on Earth, but break down at galactic scales. Maybe at very large distances or very small accelerations, gravity becomes slightly stronger than we expect. If you tweak the equations just right, you can make galaxies rotate the way Vera Rubin observed without needing any dark matter at all. The stars at the edges of galaxies move fast, not because there's invisible mass pulling on them, but because gravity itself works differently out there. It's an appealing idea. Occam's razor, the principle that simpler explanations are generally better, seems to favor it. Why invent an entirely new type of matter when you could just modify the laws of gravity slightly? But here's the problem. The universe is not obligated to be simple. And when you look at a wide range of observations, not just galaxy rotation curves, but galaxy clusters, gravitational lensing, the cosmic microwave background, the large-scale structure of the universe, modified gravity theories struggle. You end up needing different modifications for different phenomena. You lose the elegant simplicity that made the theory attractive in the first place. Meanwhile, dark matter, despite our inability to detect the particles directly, keeps working. One simple assumption, that there's a new type of matter that only interacts gravitationally, explains galaxy rotation curves, cluster dynamics, gravitational lensing, the cosmic microwave background, and structure formation in the early universe. It's consistent across vastly different scales and phenomena. So most physicists have concluded the dark matter, strange as it is real. But the modified gravity proponents haven't given up. They continue to refine their theories to look for places where dark matter might fail and modified gravity might succeed. And you know what? That's how science should work. The dark matter hypothesis should be challenged, tested, pushed to its limits. Maybe it will hold up to every test. That seems likely at this point. Or maybe, just maybe, there's some crucial observation that will reveal a flaw, that will show us we've been thinking about this wrong all along. That's happened before in physics. Classical mechanics worked beautifully until we looked at very high speeds and very strong gravitational fields. Then we needed relativity. Relativity and classical mechanics both worked until we looked at the atomic scale. Then we needed quantum mechanics. Maybe dark matter is real, but maybe it's also a sign that we're missing something deeper, something more fundamental about how the universe works. Time will tell. As for dark energy, the alternatives are even more speculative. Some theories suggest we live in a multiverse, and dark energy is actually the result of our universe interacting with other universes nearby. Some suggest that space itself has multiple dimensions we can't perceive, and dark energy emerges from the geometry of those higher dimensions. One particularly wild idea? We live in a simulation, and dark energy is essentially the programming language of the simulator, the background code that makes the whole thing run. The universe is a computer program, and dark energy is the processor clock speed. I'm not suggesting that last one is true. It's almost certainly not. But isn't it fascinating that we're forced to consider such radical possibilities? That the evidence has led us to a place where even ideas that sound like science fiction have to be taken at least somewhat seriously. We're in truly uncharted territory. We're beyond the edge of the map where medieval cartographers would write, "Here be dragons." Except our dragons are invisible, and they make up 95% of everything. Let's zoom out now. Let's look at the universe on the largest scales possible and see how dark matter shapes the cosmos. If you could see dark matter, if you had special glasses that made the invisible visible, the universe would look like a vast cosmic web, filaments of dark matter stretching across hundreds of millions of light years, connecting galaxy clusters like strings connecting pearls. Where the filaments intersect, massive knots of dark matter, and at those knots, clusters and superclusters of galaxies. Between the filaments, vast empty voids, regions of space hundreds of millions of light years across containing almost no matter otherwise. The universe has texture, structure, on scales that dwarf individual galaxies. And this structure, this cosmic web, was created by dark matter. Here's how it happened. In the beginning, right after the Big Bang, the universe was almost perfectly smooth. Almost. There were tiny variations in density, quantum fluctuations that got inflated to cosmic scales during the first fraction of a second of existence. In some places, there was slightly more dark matter. In other places, slightly less. Those tiny variations, we're talking differences of 1 part in 100,000, were enough. Gravity amplified them. Regions with slightly more dark matter pulled in more dark matter from the surrounding space. As they grew denser, their gravity became stronger, pulling in even more matter. Ordinary matter, the atoms that would eventually form stars and planets and you and me, followed along. It fell into the gravitational wells created by dark matter, flowing along the filaments, pooling at the intersections. Without dark matter, this couldn't have happened fast enough. Ordinary matter, by itself, wouldn't have clumped together quickly enough to form the first galaxies in the early universe. We see galaxies that existed when the universe was only a few 100 million years old. There simply wasn't enough time for ordinary matter alone to gather into such structures. But with dark matter, which could start clumping even before the universe cooled enough for ordinary matter to condense, there was enough gravitational pull. The scaffolding was built first invisibly, and then ordinary matter filled it in, lighting it up with stars. Every galaxy you've ever seen, including our own Milky Way galaxy, has a dark matter halo extending perhaps 100,000 light years beyond the visible disk of stars. If you could see it, It would look like a vast, diffuse sphere, denser in the center, becoming increasingly tenuous as you move outward. And we're inside it, swimming through it, orbiting the galactic center along with billions of dark matter particles we'll never detect. Right now, as you listen to this, dark matter particles are passing through you. Millions of them every second, maybe billions depending on which dark matter candidate is correct. They zip through your body, through the Earth, through the sun, through everything, almost never interacting, almost never leaving a trace. You are, in a very real sense, made of stardust. Atoms forged in the hearts of ancient stars that exploded and scattered their ashes across space. Every atom of calcium in your bones, every iron atom in your blood was created in a stellar furnace billions of years ago. But you're also surrounded by dark matter, held in place by its gravity, shaped by its presence. Your very existence, the planet you stand on, the star you orbit, the galaxy you call home, depends on the invisible scaffolding of dark matter. Doesn't that change how you think about yourself, about your place in the universe? You're not just made of star stuff, you're embedded in a cosmic web of the invisible and the unknown. So, where do we go from here? What's the future of our understanding of dark matter and dark energy? Let's start with dark matter. The search continues, more determined than ever. New detectors are being built, each more sensitive than the last. Scientists are trying different approaches, different technologies, different locations. There's a new generation of experiments coming online. Detectors using tons of liquid xenon or argon, watched by thousands of sensors, sitting kilometers underground, waiting for that one single dark matter particle to interact. Each experiment represents hundreds of millions of dollars, decades of planning, and the dedicated work of hundreds of scientists. There are also efforts to create dark matter in particle colliders. If dark matter particles exist, and if they're not too massive, then maybe we can produce them by smashing ordinary particles together at high enough energies. The Large Hadron Collider at CERN is looking for signs of dark matter in every collision, analyzing petabytes of data, searching for anomalies that might indicate dark matter creation. And there are astronomical searches too. New telescopes coming online, like the James Webb Space Telescope already sending back stunning images, and future ground-based telescopes with mirrors the size of swimming pools, will let us study the distribution of dark matter across the universe with unprecedented precision. Maybe one of these approaches will work. Maybe in 5 years, or 10 years, or 20, there will be a press conference announcing, "We've found it! We've detected dark matter particles directly." Scientists will show graphs and data, and everyone will cheer, and will move from inferring dark matter's existence to directly confirming it. Or maybe not. Maybe dark matter will continue to elude us. Maybe the particles interact so weakly or are so different from what we imagine that direct detection is impossible with any technology we can conceive. And if that happens, if we search for another 50 years and find nothing, then maybe, physicists will start to take the alternative theories more seriously. Maybe we'll circle back to modified gravity or to some completely new theory we haven't thought of yet. As for dark energy, the mystery is even deeper. We don't really have any good ideas for what it might be beyond the energy of empty space itself. We don't know how to detect it directly. We can only measure its effects on the expansion of the universe. But we're getting better at that measurement. Future surveys will map the positions of billions of galaxies, measuring how the universe's expansion rate has changed over cosmic history with incredible precision. Maybe that data will reveal some clue, some pattern that doesn't fit with the simple cosmological constant idea. Maybe it will point us toward a deeper understanding. Or maybe dark energy will remain a mystery indefinitely. Maybe it's something so fundamental, so woven into the fabric of space-time itself that we can never truly understand it from our perspective within the universe. That would be humbling, but it would also be oddly comforting. It would mean the universe still has secrets it will never reveal to us. It would mean there's always something more to wonder about. And in the meantime, we can watch what dark energy does to the universe's fate. Because here's the thing about dark energy. It's not just a curiosity. It's not just an interesting puzzle for physicists. It's determining the ultimate fate of everything that exists. If dark energy continues to accelerate, and current measurements suggest it will, then the universe is headed toward what cosmologists call the Big Freeze, or sometimes the heat death. Here's what that means. As the universe expands faster and faster, galaxies that aren't gravitationally bound to each other will move apart. First, distant galaxy clusters will disappear from view, their light stretched to undetectable wavelengths by the ever-expanding space between us and them. Then nearby galaxy clusters will vanish. Then individual galaxies. Eventually, billions of years from now, an observer in the Milky Way, which will have merged with Andromeda by then, will look up and see nothing. No other galaxies. Just the stars of their own galaxy. And beyond them, darkness. The entire observable universe will have shrunk to just one galaxy island, alone in an endless dark sea. And then stars will continue to die. Eventually, even the longest-lived stars will burn out. The universe will go dark. Black holes will swallow what remains. And then, over timescales so long they're almost meaningless, 10 to the power of 100 years, maybe more, even the black holes will evaporate through Hawking radiation. In the end, there will be nothing but empty space, expanding forever, growing colder and colder as it spreads, approaching but never quite reaching absolute zero. A universe of maximum entropy, where nothing can happen because there's no energy gradient left to drive any process. The ultimate triumph of dark energy. A universe empty and cold and still. It's a bleak picture, isn't it? And yet, there's something beautiful about it too. The universe isn't eternal. Nothing is eternal. Even the cosmos itself has a story with a beginning, a middle, and an end. We just happen to be living in the interesting part of the story. We're here during the age of stars and galaxies, when the universe is alive with light and complexity, when matter can organize itself into planets and life and consciousness. We're here in the brief cosmic moment when the universe can look at itself and wonder. And that's a gift. A temporary gift, perhaps, but a gift nonetheless.
Let's talk about the people who study these mysteries. Not just their discoveries, but who they are. What drives someone to dedicate their life to searching for something invisible? I think about researchers like Elena Aprile, who leads the xenon dark matter experiment in Italy. She's been searching for dark matter for over 20 years now. 20 years of proposal writing, detector building, data analysis, and finding nothing. Nothing definitive, anyway. What keeps someone going in the face of such uncertainty? How do you wake up every morning and choose to continue searching for something that might not even be detectable? I imagine it's a kind of faith. Not religious faith, but faith in the process of science itself. Faith that asking questions and carefully seeking answers has value, even if the answers remain elusive. Faith that the journey matters as much as the destination. There's a researcher named Priyambada Natarajan at Yale who studies dark matter through gravitational lensing. She maps how dark matter bends light from distant galaxies, creating distorted images that reveal the distribution of invisible mass. Her work requires patience, years of careful observation, mathematical modeling, comparison of predictions with data. She once said something that stuck with me. She said, "We're building a map of something we can't see using shadows and echoes. It's like being blind and understanding the shape of a room by how sounds reflect off its walls." That's what all of this is, really. We're blind to dark matter and dark energy directly. We're trying to understand vast cosmic structures through indirect effects, through mathematical inference, through the shadows they cast on things we can see. It's detective work on a cosmic scale, and it requires a particular kind of mind, patient, careful, creative, willing to sit with uncertainty for years or decades. Think about Vera Rubin again. She measured galaxy after galaxy, rotation curve after rotation curve, building an overwhelming body of evidence one data point at a time. night after night in the observatory, year after year. It wasn't glamorous, it wasn't quick, it was methodical, careful science. And she almost didn't get to do it. As a woman in astronomy in the mid-20th century, she faced discrimination at every turn. When she first started using the Palomar Observatory in the 1960s, there was no women's restroom because no one expected women astronomers. She cut a piece of paper into a skirt shape and taped it to the figure on the men's room door. She fought for every hour of telescope time, every opportunity to do research, and she did it not just for herself, but for the women who would come after her. By the time she died in 2016, she'd trained dozens of students, many of them women, who went on to become leading astronomers themselves. She'd helped open doors that had been closed, and she'd fundamentally changed our understanding of the universe. There's something deeply human about these stories. These aren't remote, godlike intellects dispensing wisdom from on high. These are people. People with doubts and frustrations and setbacks. People who faced obstacles and persevered. People who made mistakes and learned from them. Science at its best is a deeply human endeavor. It's driven by curiosity, by wonder, by the desire to understand. And it progresses not through solitary genius, but through collaboration, through communities of researchers building on each other's work, checking each other's results, arguing and debating, and slowly, collectively, moving toward truth. The search for dark matter involves thousands of scientists across dozens of countries. The experiments require international collaboration. Italian physicists working with American engineers, working with Chinese theorists, working with British data analysts. It's humanity at its best, working together toward a common goal. And what motivates all these people? Not money. There's no fortune to be made in dark matter research. Not fame. Maybe a handful of names will be remembered if the discovery is made, but most will remain unknown to the general public. No, what motivates them is simpler and purer. They want to know. They want to understand. They look up at the night sky and feel what humans have felt for thousands of years. Wonder, awe, curiosity. And they want to satisfy that curiosity. Isn't that beautiful? In a universe that's 95% invisible mystery, in a cosmos indifferent to our existence, humans keep looking, keep searching, keep trying to understand. We can't help ourselves. It's in our nature. We're nearing the end of our journey tonight, but before we close, I want to bring this back to you, back to us, back to what it means to be human in a universe dominated by darkness. You've probably heard the famous Carl Sagan quote, "We are made of star stuff." It's beautiful and true. The atoms in your body were forged in the hearts of ancient stars. The calcium in your bones, the iron in your blood, the carbon in your DNA, all of it created in stellar furnaces billions of years ago and scattered across space when those stars died. But now we know something more. We know that the universe is mostly not star stuff. It's dark stuff, unknown stuff, invisible stuff that we don't understand and may never fully understand. So what does that make us? We are rare, incredibly, impossibly rare. Ordinary matter, the stuff of stars and planets and life, makes up less than 5% of the universe. And life, complex, conscious life, that's rarer still. As far as we know, Earth might be the only place in the entire observable universe where matter has organized itself into consciousness. We are the universe's way of knowing itself, as Sagan also said. But we're a tiny, fragile, temporary way. We're like brief candles flickering in an endless dark. But we shine. We look out at that darkness and we try to understand it. We build telescopes and theories and experiments. We spend our brief lifetimes, these cosmically insignificant moments, trying to comprehend the infinite. That's something both tragic and heroic. Tragic because we'll never fully succeed. The universe is too big, too strange, too unknowable. We're 3-pound lumps of organized matter trying to understand the fundamental nature of reality. We're limited by our biology, by our lifespans, by the sheer scale of what we're trying to comprehend. We will die with questions unanswered. Humanity itself will eventually end, long before the universe does, with mysteries still unsolved. But it's heroic, too. Because we try anyway. Knowing we can't fully succeed, we keep looking, keep questioning, keep searching. We refuse to accept ignorance. We refuse to stop asking why and how. We look at a universe that's 95% invisible and say, challenge accepted. I find that inspiring. On difficult days when the world feels overwhelming, when personal struggles feel insurmountable, I remember that humans are the kind of creatures that look at galaxies spinning impossibly fast and don't just throw up their hands in defeat. We invent dark matter. We design experiments. We spend decades searching. We don't give up on understanding, even when understanding seems impossible. And there's something else I find comforting about dark matter and dark energy. They remind us that we don't know everything, that the universe still holds secrets, that there's still mystery left in the world. In an age where it sometimes feels like everything has been discovered, every corner of the earth explored, every question answered by a quick internet search, dark matter whispers, not yet. Not even close. There's still so much you don't know. That's not depressing. That's exciting. It means there's still room for wonder, still room for discovery, still questions worth asking. Maybe you'll never detect a dark matter particle. Maybe you'll never solve the mystery of dark energy. But you can look up at the night sky and know that you're seeing only a tiny fraction of what's there. Let me tell you one more story. It's about Werner Heisenberg, one of the founders of quantum mechanics. Heisenberg was hiking in the mountains with his friend and colleague Niels Bohr, and they were discussing the strange implications of quantum theory. At one point, Heisenberg became frustrated. The more we study matter, he said, the stranger it becomes. Particles that are also waves, objects that don't have definite properties until we observe them. It's maddening. Can we ever really understand the universe? Bohr stopped walking and looked at him. Werner, he said, you're not thinking clearly. We're part of the universe. The universe is trying to understand itself through us. Of course it seems strange. How could it be otherwise? I think about that story often when contemplating dark matter and dark energy. We want the universe to make sense on our terms. We want it to be comprehensible to human minds, to fit into categories we can grasp, to follow rules that seem intuitive. But why should it? The universe wasn't made for us. It doesn't owe us comprehensibility. It just is what it is. And we're trying to understand it using brains that evolved to help hunter-gatherers find food and avoid predators on the African savanna. It's actually remarkable that we can understand as much as we do, that mathematics, abstract patterns of thought, somehow describes reality. That we can look at the red shift of distant supernovae and calculate the fate of the universe. That we can infer the existence of invisible matter from galaxy rotation curves. We've come so far from our ancestors who looked up at the stars and saw gods and heroes. We've learned about nuclear fusion and relativity and quantum mechanics. We've sent robots to other planets and telescopes beyond our solar system. We've measured the age of the universe within a few tens of millions of years. And yet, 95% remains dark to us. Maybe that ratio will never change. Maybe we're fundamentally limited in what we can know. Maybe dark matter and dark energy are like the sound of one hand clapping or the color that lies beyond ultraviolet. Things that cannot, even in principle, be directly perceived or fully understood by beings like us. Or maybe tomorrow, someone in a laboratory will see something unexpected. A flash of light in a xenon detector, an anomaly in particle collider data, a pattern in astronomical observations that doesn't fit any existing model. And that will be the beginning of a new understanding, a new chapter in the cosmic story. That's the thing about science. You never know when breakthrough will come. You never know which experiment, which observation, which careful analysis will crack open a mystery that's persisted for decades. It could be tomorrow. It could be 100 years from now. It might never come. But the search continues because the search itself has value. Because trying to understand is part of what makes us human. Tonight, after you finish listening to this, I want you to do something. Go outside. Find a place away from bright lights if you can. And look up. Look at the stars. Not at your phone, not at a screen. Actually look up at the real sky above you. What you're seeing is ancient light. The stars you see are so far away that their light has been traveling for years, decades, centuries to reach your eyes. You're literally looking back in time. That photon hitting your retina right now left its parent star when your grandparents were young, or when Napoleon was alive, or when humans hadn't even invented writing yet. But that's just the ordinary matter. The visible stuff. Now imagine what you can't see. Imagine the dark matter halo surrounding our galaxy, the invisible cloud we're embedded in. Imagine dark matter particles streaming through you right now, trillions of them, every second, each one passing through your body without leaving a trace. Imagine the fabric of space itself, permeated by dark energy, slowly, inexorably, accelerating the expansion of the universe. Every second, distant galaxies are getting farther away. Every second, the universe is growing larger. You can't see it or feel it, but it's happening. You're standing on a planet that's orbiting a star, that's orbiting a galaxy center, that's held together by gravity from invisible matter that we've spent nearly a century searching for without success. You're living in a universe where everything you see is the rare exception, the unusual stuff, the mere 5%. How does that feel? For me, It feels like perspective, like a gentle reminder not to take myself too seriously, like an invitation to wonder. All the things we worry about, the small dramas of daily life, the social anxieties, the career concerns, the petty conflicts, they seem both more manageable and more precious when viewed against the backdrop of cosmic mystery. More manageable because, in the grand scheme of things, they don't matter much. The universe doesn't care whether you got that promotion, or whether that person likes you, or whether you said something awkward at a party last week. It's going to continue expanding regardless, indifferent to human concerns, but also more precious because they're yours, because consciousness, the ability to worry, to hope, to love, to dream, is rare and valuable and temporary. Because you get this brief moment to exist, to experience, to matter to other conscious beings before you return to the atoms that make you up, and those atoms eventually return to the cosmos. Dark matter and dark energy remind us of our place in the universe. Tiny, temporary, but also unique and precious. We're rare stuff in a universe of darkness. We're the universe's way, perhaps its only way in this corner of space, of understanding itself. So when you look up at the stars tonight, feel small if you want. That's okay. It's appropriate. We are small. But also feel wonder. Feel curiosity. Feel the same urge that drove Vera Rubin to measure galaxies night after night, that drives physicists to build detectors deep underground, that has driven humans for millennia to look up and ask, what is all this? How does it work? Why is it here? Those questions don't have complete answers yet. They may never have complete answers. But asking them, that's what makes us human. There's a particular kind of beauty in the invisible, don't you think? Consider this. Dark matter has never been directly observed. We don't know what it looks like, what it's made of, what it feels like. It exists for us only as mathematics, as graphs and charts and equations. It's purely abstract. And yet, it's everywhere. It's the scaffold on which galaxies hang. It's the invisible architecture of the cosmos. It's more common than stars. There's something almost mystical about that. Something that borders on poetry. The ancient mystics spoke of hidden realities, of divine presences that couldn't be seen but could be felt through their effects on the world. They spoke of the wind as evidence of the invisible, of shadows as proof of light we cannot look at directly. Dark matter is like that. It's the modern universe's way of teaching us the same lesson, that reality is deeper than what we can see, that there are truths beyond direct perception, that faith in mathematics, in scientific method, in the consistency of natural law, can reveal what sight cannot. I'm not trying to make dark matter into something religious. Science and religion are different. Let me share some conversations I've had, imaginatively, with the ghosts of science, with the spirits of Fritz Zwicky and Vera Rubin, and all the others who've grappled with these mysteries. I imagine meeting Fritz Zwicky first, that difficult Swiss astronomer who discovered dark matter almost by accident. He's standing at his telescope on Mount Wilson, and I ask him, "Did you know? Did you understand what you'd found?" He laughs, that sharp, barking laugh of his. "No, of course I knew. I did the mathematics.
The galaxies were moving too fast. Simple as that. But did anyone listen? Did anyone care? They thought I was crazy. They thought I was arrogant. Maybe I was both, but I was also right. I asked him how it felt, being right and being ignored. He's quiet for a moment. Lonely, he finally says. Science is supposed to be about truth, about evidence, about logic, but scientists are human. They have egos, they have prejudices. Sometimes the truth has to wait for politics to catch up. Then I'm with Vera Rubin, decades later, at the Palomar Observatory. The night is clear and cold. She's at the spectrograph, carefully measuring the rotation of another galaxy. Why do you do this? I ask her. Night after night, galaxy after galaxy. Doesn't it get tedious? She smiles. Tedious? No. Every galaxy is different. Every rotation curve tells a story, and all together, they're telling us something profound about the universe. How could that be tedious? But the discrimination, I press. The obstacles, the doors that were closed to you. How did you keep going? Her smile fades a bit. I had a choice, she says quietly. I could let the obstacles stop me, or I could work around them. I chose to work around them, not just for me, for my daughters, for all the young women who would come after me. Someone had to push open the doors. Someone had to show that women could do this work just as well as men. Why not me? Then I'm in a modern laboratory, deep underground. A young physicist, no one famous yet, no one whose name you'd recognize, is monitoring detectors, searching for dark matter. Shift after shift, week after week, watching for a signal that hasn't come. Are you discouraged? She shrugs, sometimes. But that's not really the point. Someone has to do this work. Someone has to build the detectors, take the data, do the analysis. Maybe I'll be the one who detects it. Maybe I won't. Maybe it'll be someone in another experiment, another country 10 years from now. But my work will be part of that discovery, even if I'm just a footnote. That's enough for you? She thinks about it. Yeah, it is. I get to work on the biggest mystery in physics. I get to be part of something larger than myself. Not everyone gets that. I'm lucky. These conversations are imaginary, of course, but they capture something true about the scientific spirit, about the kind of people who dedicate their lives to understanding the universe. They're not in it for glory, though glory would be nice. They're not in it for certainty. There is no certainty at the frontier of knowledge. They're in it because they can't help themselves, because they look at the universe and see mystery and feel an overwhelming need to understand. That's the human spirit at its best. That's what we're capable of when we're not tearing each other down, when we're not fighting over resources or territory or ideology. We're capable of wonder. We're capable of curiosity. We're capable of working together to answer questions that benefit all of humanity, not just one nation or one group. Dark matter research is international. Scientists from every continent, from dozens of countries, with different languages and cultures and political systems, all working on the same problem. Not because they have to, because they want to. That gives me hope. In a world that often seems divided, fractured, filled with conflict, the search for dark matter reminds us that we can still come together around shared curiosity, shared wonder, shared humanity. What does the dark side of the universe teach us? What lessons can we draw from these invisible mysteries? First, humility. The universe is under no obligation to make sense to us. It doesn't care about our intuitions or expectations, our need for comprehension. It simply is what it is, and most of what it is, we can't even see. That's a powerful lesson in humility. We think we're so smart, and we are, relatively speaking. We've accomplished remarkable things, but 95% of the universe remains dark to us.
We're like children who've learned to count to 10 and think we understand mathematics. Second, patience. Dark matter was proposed in 1933. It wasn't widely accepted until the 1980s, half a century later, and we still haven't detected it directly. Another 40 years on. That's more than a human lifetime spent on a single problem. Science doesn't move at the pace we'd like. Mysteries don't solve themselves on our schedule. Understanding requires patience, persistence, and the willingness to keep working even when progress seems impossible. Third, wonder. In an age of instant information where we can find answers to almost any question with a quick search, dark matter and dark energy remind us that some questions remain unanswered. Some mysteries persist. There's still room in the universe for genuine wonder, genuine not knowing. That's precious. Wonder is what drives discovery. Certainty, paradoxically, is the enemy of knowledge. When we think we know everything, we stop looking, stop questioning, stop growing. The dark side of the universe keeps us humble, keeps us patient, keeps us wondering. And those are good things to be. Fourth, interconnectedness. Your body is made of atoms forged in stars. Those atoms are held together by forces we understand pretty well. You're standing on a planet held in orbit by gravity. That planet orbits a star in a galaxy held together by dark matter. The galaxy exists in an expanding universe driven by dark energy. You're not separate from any of this. You're part of it. The same physical laws that govern galaxies govern your heartbeat. The same forces that structure the cosmic web structured the proteins in your cells. You're connected to everything, all the way up and all the way down. Understanding that can change how you see yourself. You're not an isolated individual struggling alone against an uncaring universe. You're an integral part of that universe, made of its substance, following its laws, participating in its great unfolding story. Finally, hope. Even though we don't understand dark matter and dark energy, we keep looking, we keep searching, we don't give up. That persistence, that refusal to accept ignorance, that determination to understand, that's the best of what it means to be human. And if we can bring that same determination to other problems, to climate change, to inequality, to conflict, to all the challenges facing humanity, then maybe we have a chance. Maybe we can solve those problems too. The universe teaches us that mysteries can be approached systematically, that careful observation and clever thinking can reveal truths that seemed impossibly hidden. It teaches us that collaboration works better than competition, that diverse perspectives strengthen understanding, that patience and persistence pay off over time. Those lessons apply to more than just physics. They apply to life. Here's something that might seem strange. I'm glad we don't fully understand dark matter and dark energy. I'm glad there are still mysteries. Not because I want scientists to suffer or fail, not because I don't value knowledge, but because a universe fully understood would be a universe with no room for wonder, no room for discovery, no room for that delicious feeling of standing at the edge of knowledge and peering into the unknown. Imagine if we knew everything. Imagine if every question had an answer, every mystery was solved, every corner of reality was mapped and measured and explained. What would be left to discover? What would drive us forward? We'd stagnate. We'd lose something essential about what makes us human, that drive to explore, to question, to seek. The unknown is a gift. The darkness is an invitation. Think about children. What makes childhood magical? It's not knowledge. Children don't know much. It's wonder. It's the sense that the world is full of mysteries waiting to be discovered. Everything is new. Everything is possible. Around every corner could be something amazing. As adults, we often lose that. We think we know how things work. We settle into routines. The world becomes predictable, comprehensible, even boring. But dark matter and dark energy give us back a little of that childhood wonder. They remind us that we don't know, that the universe is still full of mysteries, that reality is stranger than we imagined. And that's exciting. That's energizing. That's a reason to get up in the morning and look at the world with fresh eyes. The uncertainty isn't a bug, it's a feature. It's what keeps life interesting. Of course, there is a balance. Too much uncertainty becomes anxiety. If we knew nothing, if everything was mysterious, we couldn't function. We need some degree of understanding to navigate the world. But we also need some mystery. We need to know that there are things we don't yet understand, questions we haven't yet answered, discoveries waiting to be made. Dark matter and dark energy give us that. They're the universe's way of saying, you've learned a lot, you've come far, but there's still so much more. Keep looking, keep wondering, keep seeking. And we do, because we can't help ourselves, because wonder is hardwired into us. If the universe could speak to us directly, what would it say about its dark side? I imagine it would say something like this. Yes, I am mostly invisible to you. 95% of me is beyond your direct perception. But isn't that appropriate? You are such small beings, living such brief lives. Should all of reality be comprehensible to creatures that exist for less than a cosmic eye blink? I have revealed to you what you needed to survive. The electromagnetic spectrum you can see, a tiny slice of all possible wavelengths, is perfectly calibrated to let you navigate your world. You can see the sun, the moon, the stars. You can see food and predators and each other. That's enough for survival. But you wanted more than survival. You wanted understanding. So you built tools, telescopes and spectrographs and detectors to extend your senses. You developed mathematics to see patterns your eyes cannot perceive. You created the scientific method to uncover truth. And I rewarded your curiosity. I showed you atoms and galaxies. I revealed relativity and quantum mechanics. I let you glimpse the Big Bang, the cosmic microwave background, the expansion of space itself. But I also showed you your limits. Dark matter and dark energy are my way of teaching you humility. You know so much, yes, but you don't know everything. You may never know everything, and that's okay. The joy is in the seeking, not just in the finding. The value is in the journey, not just the destination. You are at your best when you're reaching beyond your grasp, when you're trying to understand what seems incomprehensible, when you're standing at the edge of your knowledge and daring to leap into the unknown. So yes, I am mostly dark to you, but that darkness is not your enemy, it's your invitation. It's calling you forward, calling you deeper, calling you to become more than you are. Keep looking, keep wondering, keep seeking. That's what consciousness is for. That's what you're here to do. Is that presumptuous, to imagine the universe speaking? Maybe. The universe probably doesn't have intentions or messages. It just is. But we create meaning through interpretation. We find significance in our observations. That's what humans do. We're pattern-seeking, storytelling creatures. We can't help but find meaning even in the impersonal mechanics of physics. And if we're going to find meaning in dark matter and dark energy, let it be this. We're being invited to grow, to expand our understanding, to reach beyond our current limitations. That's a beautiful message to receive from the cosmos. That's a story worth telling. You might be wondering, okay, this is all very philosophical and poetic, but what does it actually matter? How does dark matter and dark energy affect my daily life? The honest answer is directly, not at all. You can live your entire life without ever thinking about dark matter and be perfectly fine. Your car will still run, your food will still taste good, the sun will still rise. Dark matter research won't cure cancer or solve climate change or put food on anyone's table in the immediate future. But that's a narrow way to think about value. First, there's the practical reality that fundamental research often has unpredictable applications.
When scientists first studied electromagnetism in the 1800s, they weren't thinking about smartphones and Wi-Fi and MRI machines. When Einstein developed relativity, he wasn't imagining GPS satellites that need relativistic corrections to work properly. When quantum mechanics was being worked out, no one saw computer chips and lasers and LED lights. The search for dark matter has already driven innovation. The sensitive detectors being developed have applications in medical imaging. The data analysis techniques transferred to other fields. The international collaborations create networks of knowledge sharing that strengthen science globally. Who knows what technologies might emerge from finally understanding dark matter? Maybe nothing. Maybe something revolutionary. We can't know until we get there. Second, there's the cultural and philosophical value. We are not just bodies that need feeding and sheltering. We're conscious beings with a drive to understand, to create meaning, to connect with something larger than ourselves. Art doesn't keep you alive, but life without art is impoverished. Music doesn't feed you, but a world without music would be diminished. Philosophy doesn't pay the bills, but a society that never asks deep questions about meaning and purpose and truth is shallow. Science, especially fundamental science, serves a similar function. It enriches human culture. It expands our understanding of our place in the cosmos. It gives us perspective on our lives and our problems. It connects us to something vast and ancient and ongoing. That has value. Maybe not dollar value, but human value, spiritual value, if you want to call it that. Third, there's the simple fact that a civilization that stops exploring, that stops questioning, that stops seeking to understand the universe is a civilization in decline. Curiosity is what drives progress, not just technological progress, but moral and philosophical progress too. When we ask, what is the universe made of? We're also implicitly asking, what are we? Where did we come from? Where are we going? Those are profound questions. They matter. And finally, there's inspiration. Every time a major discovery is made in physics or astronomy, children get excited. They look up at the sky with wonder. Some of them decide to become scientists. Some of them become engineers or artists inspired by the cosmos. The search for dark matter keeps that pipeline flowing. It keeps the fire of curiosity burning. It shows young people that there are still mysteries to solve, still frontiers to explore, still questions worth asking. That's valuable. That's worth investing in. Not because it'll pay immediate dividends, but because a society that values curiosity and exploration is a healthier, richer, more vibrant society than one that doesn't. So, yes, dark matter won't directly affect your daily life, but it affects the kind of civilization we are, the values we hold, the legacy we leave to future generations. And that matters more than most people realize.
Throughout history, humans have told stories to explain the darkness. Ancient peoples saw gods and monsters in the night sky. The Greeks imagined constellations, heroes and animals frozen in eternal patterns. Norse mythology spoke of Fenrir, the wolf who would swallow the sun during Ragnarok. Many cultures had creation myths that began with darkness, with void, with nothing. And then light emerged to create the world. These weren't just stories. They were ways of understanding, ways of creating meaning from mystery, ways of making the vast, incomprehensible cosmos feel a little more manageable. We do the same thing today, just with different tools. We tell stories with mathematics instead of mythology. We create meaning through scientific theories instead of creation myths. But the impulse is the same. We're trying to understand the darkness, to explain it, to make it less frightening. Dark matter and dark energy are our modern mysteries, our contemporary darkness. And we're doing what humans have always done. We're shining light into it, trying to illuminate it, trying to understand it. But here's what's different. We're okay with not having all the answers right away. Ancient mythologies provided complete explanations immediately. The Greeks didn't say, "We're not sure what causes lightning, but we're working on some hypotheses."
They said, "It's Zeus throwing thunderbolts." And that was that. Science is more patient, more humble, more willing to say, "We don't know yet, but we're looking. We have some ideas, we're testing them. Check back in a few decades." That's progress, in a way. Not just in our understanding of the universe, but in our relationship with uncertainty. We've learned to sit with not knowing, to be comfortable with mystery while still working to resolve it. That's a mature relationship with the unknown. That's psychological and spiritual growth, not just scientific progress. And maybe that's one of the most important lessons dark matter and dark energy teach us. It's okay not to know everything right away. It's okay to have questions without immediate answers. Uncertainty isn't weakness, it's honesty. Mystery isn't failure, it's opportunity. The stories we tell ourselves about the darkness have changed, but the darkness itself remains. Always has, always will. And that's beautiful. That's as it should be. Because if we solved every mystery, answered every question, illuminated every shadow, what would be left? Where would we go from there? No, it's better this way. It's better to live in a universe that still surprises us, still challenges us, still invites us deeper. Let's do something different now. Let's try to really feel what it means to be embedded in this cosmic web of darkness. Close your eyes if you're not driving or doing anything that requires vision. I'll wait. Now, feel the chair beneath you, the floor beneath your feet. You're sitting still, right? Not moving? Wrong. You're moving. Fast. Incredibly fast. Earth is spinning on its axis at about 1,000 miles per hour at the equator. You're rotating with it, even though you feel perfectly still. Earth is also orbiting the Sun at about 67,000 miles per hour. You're flying through space, racing around our star as you sit there. The solar system is orbiting the center of the Milky Way galaxy at about 514,000 miles per hour. Everything, the sun, the planets, you, me, all of us, are swept up in this vast galactic rotation. And the Milky Way itself is moving through space, pulled by the gravitational attraction of nearby galaxy clusters, traveling at about 1.3 million miles per hour relative to the cosmic microwave background. You're not still. You're falling through space at millions of miles per hour. You're caught in nested rotations and movements, spiraling through the cosmos, held in place by gravity from matter you can see and matter you can't. Can you feel it? Can you sense that movement? Probably not directly. Our senses aren't built to perceive motion at those scales. But you can imagine it. You can visualize it. You can picture yourself as a passenger on this cosmic journey. And here's the amazing thing. You're perfectly safe. All that motion, all that speed, and you're not being thrown around. You're held in place, protected by the same forces that structure the entire universe. The dark matter halo around our galaxy, that invisible cloud we can't see, is part of what keeps us here. Its gravity contributes to the overall structure that allows Earth to exist, that allows stars to form, that allows anything stable to persist. You're floating in the invisible, swimming in the dark, and it's holding you, keeping you safe, even as you hurtle through space at speeds that would terrify you if you really grasped them. There's something deeply comforting about that, isn't there? The universe seems cold and uncaring, and in many ways it is. But it's also structured in such a way that complexity can exist, that order can emerge from chaos, that life can arise and persist. Dark matter is part of that structure. Dark energy, for all its strangeness, is part of what makes the universe habitable on cosmic scales. Its expansion prevents the universe from collapsing back in on itself, gives matter room to breathe, allows galaxies to form and evolve. You exist because the universe has certain properties, certain laws, certain structures. Dark matter and dark energy are part of that. They're part of why you're here. So when you think about them, don't just think about the mystery, the unknown, the frustrating inability to detect them directly. Also think about the fact that they're working right now, this very moment, to maintain the cosmic order that allows your existence. You're alive because of invisible things you'll never see. You're here because of forces that operate beyond human perception. You're a temporary pattern of matter and energy made possible by the deep structure of reality, visible and invisible alike. That's profound. That's worth sitting with for a moment. Somewhere right now, there's a child looking up at the night sky and wondering. Maybe they're in a city and they can only see a handful of stars through the light pollution. Maybe they're in the countryside and the Milky Way stretches above them like a river of light. Maybe they're not looking at the real sky at all, but at pictures in a book or images from a telescope online. But they're wondering. They're asking questions. Why is the sky dark? What are stars made of? How big is the universe? Are we alone? Maybe that child will become the scientist who finally detects dark matter. Maybe they'll develop a theory that explains dark energy. Maybe they'll make a discovery we can't even imagine yet, something that revolutionizes our understanding of reality. Or maybe they won't. Maybe they'll become a teacher who inspires other children to ask questions. Maybe they'll become an engineer who builds the next generation of detectors. Maybe they'll become an artist who creates works inspired by cosmic mystery. All of those are valuable. All of those contribute to humanity's ongoing dialogue with the universe. The point is, the search continues. The mystery endures. And each generation inherits it from the last, works on it with the tools available to them, and passes it forward to the next. That continuity is beautiful. That's human civilization at its best, accumulating knowledge across generations, building on what came before, reaching ever higher toward understanding. We're part of that chain, not just scientists, all of us. Because even if we're not actively researching dark matter and dark energy, we're part of the culture that values science, that funds research, that celebrates discovery. We're part of the civilization that looks up at the night sky and refuses to accept ignorance. And the children watching us, whether they're our own children or just the next generation coming up, they're learning from our example. They're learning whether curiosity is valued, whether questions are encouraged, whether mysteries are exciting opportunities or frustrating obstacles. What we do matters. How we talk about science matters. Whether we support research, whether we celebrate discovery, whether we maintain our sense of wonder, all of that shapes the future. So when you think about dark matter and dark energy, think not just about the current state of knowledge, but about the children who will inherit these mysteries. What kind of world are we creating for them? What kind of legacy are we leaving for them? Will they live in a world that values understanding, that invests in curiosity, that sees cosmic mystery as an invitation rather than a threat? That's up to us. That's our choice. That's our contribution to the ongoing human project of trying to understand the universe.
What would dark matter sound like if we could hear it? That's a strange question, I know. Dark matter doesn't make sound. Sound requires vibrating molecules, and dark matter barely interacts with regular matter at all. But bear with me. Let's imagine. Maybe it would sound like silence. Deep, profound silence. The kind of silence you experience in a soundproof room or deep underground. A silence so complete it's almost oppressive, almost physical. That absence of sound, that void, that could be dark matter. Present but imperceptible. There but not there. Or maybe it would sound like wind, like the rush of air through empty space, not loud, but constant. A background hum that's always there, but that you only notice when you really listen. That could be the dark matter particles streaming through you right now, billions per second, each one a whisper in the cosmic wind. Or maybe, and this is my favorite idea, maybe it would sound like a chord, like multiple notes played simultaneously, creating harmony. Each frequency representing a different aspect of reality, the electromagnetic spectrum we can see, the gravitational waves we recently learned to detect, the neutrinos constantly passing through us, and underneath it all, the deep bass note of dark matter, the foundation that holds everything together. Musicians talk about the fundamental note, the lowest frequency in a harmonic series that gives a sound its character. Without the fundamental, the overtones sound thin, incomplete. Maybe dark matter is the fundamental note of the universe, and everything we see and hear and measure are just the overtones, the harmonics, the elaborations on that deep, dark theme. I like that metaphor because it captures something true. Dark matter isn't separate from the visible universe. It's not some alien thing that has nothing to do with us. It's intimately connected with everything we see. It's the foundation, the structure, the cosmic scaffolding on which ordinary matter hangs. And if we could hear it, if we could somehow translate its presence into sound, maybe we'd find that it's been singing to us all along. A song we couldn't quite hear. A melody just beyond the range of human perception. That's poetic. Maybe too poetic for a scientific topic. But science and poetry aren't as different as people think. Both are attempts to capture truth, to express understanding, to create meaning from observation. Scientists use equations. Poets use metaphors. But both are reaching for the same thing, a deeper comprehension of reality. And sometimes poetry can express scientific truths that equations can't. Not better, just differently. Poetry can convey the emotional weight, the psychological impact, the existential significance of scientific discovery in ways that pure mathematics cannot. So yes, dark matter is a scientific mystery described by rotation curves and gravitational lensing and cosmic microwave background anisotropies. But it's also a cosmic silence, a background hum, a fundamental note that grounds everything else. Both descriptions are true. Both matter. As we near the end of our journey tonight, I want to reflect on what dark matter and dark energy have taught us about ourselves, about humanity, about what it means to be conscious creatures in an incomprehensible universe. First, we've learned that we're capable of extraordinary humility. It would be easy, it would be natural, to insist that we're right, that our observations must be wrong, that there's no mysterious, invisible matter permeating the universe. Our egos would prefer that. Our sense of certainty would be more comfortable with that. But instead, the scientific community looked at the evidence and said, okay, we don't understand this. There's something here we're missing. Let's figure out what it is. That willingness to admit ignorance, to accept that reality might be stranger than we thought, that's remarkable. That's mature. Second, we've learned that we're capable of sustained effort in the face of uncertainty. Scientists have been searching for dark matter for decades now with no definitive result. They keep building detectors, keep analyzing data, keep refining theories, even though success is not guaranteed, even though they might spend entire careers searching for something they never find. That persistence, that dedication to the search itself, rather than just the discovery, that says something profound about human nature at its best. We can commit to something larger than ourselves. We can work toward goals we might never personally achieve. Third, we've learned that collaboration works. The search for dark matter requires international cooperation, sharing of data, coordination of experiments. Scientists from countries that might have political tensions work together seamlessly because they share a common goal. They put aside nationalism, competition, ego, and work together. If humanity could bring that same collaborative spirit to other problems, climate change, poverty, disease, conflict,
Imagine what we could accomplish. Dark matter research shows us that we're capable of it, that it's possible, that when we're united by common purpose, we can achieve remarkable things. Fourth, we've learned that mystery is generative. Not knowing hasn't paralyzed us. It's energized us. The mystery of dark matter has driven innovation, inspired careers, created communities of researchers, generated new technologies and new theories. The darkness has been productive. That suggests something important. Problems don't have to be fully solved to be valuable. The process of working on them, thinking about them, trying to understand them, that process itself has worth. The journey matters as much as the destination. And finally, we've learned that wonder is sustainable. You might think that the more we learn, the less amazing the universe becomes, that understanding diminishes magic. But that's not what's happened. The more we learn about dark matter and dark energy, the more amazing they become. The mystery deepens rather than dissipates. The universe keeps surprising us. It keeps showing us that it's stranger, more complex, more beautiful than we imagined. And that suggests that wonder isn't a finite resource. There's always more to discover, always new questions to ask, always fresh reasons to look up at the night sky with awe. So what have we learned about ourselves? That we're humble enough to admit ignorance, persistent enough to seek answers indefinitely, collaborative enough to work across all boundaries, creative enough to be energized by mystery, and capable of sustaining wonder indefinitely. That's a pretty good summary of humanity at its best, isn't it? That's who we can be when we're engaged with something larger than ourselves. Dark matter and dark energy didn't just teach us about the universe, they taught us about ourselves. And maybe that's the most important discovery of all.